Okay, now let's find an isoquant and the marginal rate of technical substitution for this production function. And this guy over here is a Cobb-Douglas production function. Okay, so to find the isoquant, last time I chose to put k on the vertical axis, but just to sort of emphasize that you don't have to do that, I'm going to do the other way around this time. So I'm going to put L on the vertical axis and K on the horizontal. You can choose whichever one you want. And since I put L on the vertical axis this time, I'm going to solve this equation for L to get my isoquant equation. All right, so I need to get L on its own. So I have L right now multiplied by a bunch of garbage. Let's divide out that stuff to put it on the other side. So we divide both sides of the equation by everything that's not L, and we end up with Q divided by 1/3, which is the same as 3 times Q, divided by K to the 1/3 power, and that's equal to L to the 2/3 power. Now, unfortunately, we're not there yet, okay? We need to get L as a function of Q and K, not L to the 2/3. So we've got to get rid of that exponent. How do we do that? Well, we know that if we raise an exponent to a different exponent, we're going to multiply them together. And we also know that an exponent of 1 is something that you can just drop. So let's raise this thing to the power of 3/2, because multiplied together, they'll equal 1, and we'll be done. We have to do that to both sides. And now we've got 3Q over K to the 1/3 to the 3/2 power is equal to L. This is an equation that's right. It does tell us, we could plug in numbers and do it, but there's a little bit simpler way to sort of see the answer here. If we distribute this 3/2 to all of the terms, we get on the top 3Q to the 3/2 power, but on the bottom, K to the 1/3 multiplied by 3/2, the 3's cancel, and this becomes the square root of K, okay? And this is our isoquant, okay? If K is equal to, we could say, like we did in the last one, suppose we wanted to find Q equal to 30, the isoquant for that. Well, if K is equal to 0, in this case, we're dividing a positive number by 0 and we get infinity. And this gets to the idea that these production functions, when you get to the edges where one input is really scarce and the other is plentiful, the scarce input becomes super important. And in this case, when it's at 0, it's infinitely important. And we can actually see from this original production function up here that if K was ever equal to 0, no matter what L is, you're not going to produce any output, and even if it goes to infinity. So it's going to end up looking something like this. Okay, and we could calculate some actual points in here and sort of fill this out, but it's not really important for doing this exercise here. To find the marginal rate of technical substitution, there are 2 ways to go. One, we could say that the marginal rate of technical substitution is equal to the negative MPK over MPL. Or 2, we could find the slope, now that we have this equation here. So we'll do it both ways. One thing to notice is that now I wrote MRTS is equal to MPK over MPL. Why did I do that? Normally I've been writing MPL over MPK, so I've been writing this thing flipped. And that's because I flipped these axes over here. The simple way to remember it is that it's like opposite of what you would think. If L is on the vertical axis, then using this MRTS, what we're looking for is the partial derivative of L with respect to K, and they're opposite. If the L is on the top, then it's on the bottom on the other one, and vice versa. Okay, so we know we can find the marginal product of capital over here by taking the derivative of this guy here. Okay, so we multiply 1/3 by the exponent on K, which is also 1/3. Then we subtract 1 from the exponent, and we end up with negative 2/3. And then we have L to the positive 2/3. This thing is equal to 1/9. And one way to write it is L over K, all raised to the 2/3 power. Because we have L to the 2/3, k to the negative 2/3, so we can use the reciprocal rule and put it on the bottom there. Now we find MPL. It's going to look almost the same but flipped. All right, so we're going to now take 1/3 and multiply by the exponent on the L, which is 2/3. And then we have k to the 1/3, L to the 2/3 minus 1, which is negative 1/3. And we're going to get 2/9 times k over L to the 1/3 power. Okay? Now we can, these look kind of ugly, but actually it's not that bad. If we divide one by the other, we're going to get kind of a simple equation. So if we do MPK divided by MPL, we need the negative of that, we're going to have 1/9 divided by, or times L over K to the 2/3 divided by 2/9 times K over L to the 1/3. Okay? Now, since we're dividing by this, let's use our reciprocal rule and rewrite it as, I'm going to run out of space here, so I'll move it up a little bit. One-ninth divided by 2/9 is just 1/2. Then we have L over K to the 2/3 power. And since we're dividing by K over 1 to the 1/3, we can also multiply by the same thing, but raised to the power of negative 1/3. Okay? And now that we have this up here, we can kind of do the same trick again. If we're multiplying by k to the negative 1/3 power, that's the same as dividing by k to the 1/3 power. And if we're dividing by L to the negative 1/3 power, that's the same as multiplying by L to the 1/3 power. And now we can just add the exponents, because we have L to the 2/3 times L to the 1/3 divided by k to the 2/3 times k to the 1/3. This is 1/2 L over k with a negative sign in front everywhere. And that's the marginal rate of technical substitution. Notice that in this case, the marginal rate of technical substitution changes for every value of L and K, which is what you would expect looking at this figure. Okay, as you change K, the MRTS changes as well. We could also do this by finding the slope of our equation over here. So if we know that L is equal to 3Q to the 3/2 divided by K to the 1/2, we could take the derivative of this, and we get 3Q to the 3/2 over here divided by K to the 1/2. I'm sorry. There's a bit of a trick to this one. Anyway, so this is, instead of writing it down there, let's multiply it by K to the negative 1/2. And then we need to multiply this whole thing by the reciprocal. So it's negative 1/2, and subtract 1 off of that. So let me write it a little bit more clearly. Equals negative 1/2 3Q to the 3/2 power times K to the negative 3/2. So you're at first looking at this and you're thinking, these two things do not look the same, right? They look pretty different. But that's actually because one of them is expressed in terms of L and K, and the other one is expressed in terms of K and Q. If we substitute one of these things for the other, we're going to get the same thing back out. In fact, it's easiest in this case, since we know that L is equal to this, to plug this L in over here. So we have the MRTS is equal to negative 1/2 L over K, but instead of L, we're going to use this equation. We get 3Q to the 3/2 divided by K to the 1/2, and then we use this part here, divided by K. Now, we simplify that a little bit. We have we're dividing by K to the 1/2 and dividing that by K. we end up with negative 1/2 3q to the 3/2 times k to the negative 3/2, which is the same as what we got over here. Okay. Alternatively, we could have plugged in q from way up at the top here for the q in this equation right here, and we would have attained 1/2 L over K. Okay, so you can do it two different ways. It's, again, another way to check your work, but there's a little bit of extra step when the variables change, like when you're using different variables. But it is still ultimately the same value, the same equation.